This is Chapter 2, IoT Systems and Architectures. In this chapter, we'll use industry standard models to explain IoT systems. We'll explain the value of IoT industry standards. We'll explain the value of IoT industry standard models. We'll use a common model to explain IoT security, explain how a layered security model is useful in understanding IoT requirements. We'll create an IoT threat model, explain the cybersecurity job roles, and explain how threat models are constructed. Models of IoT systems.
Layered models are often used to illustrate how data communication occurs from end to end. There are many benefits to using a layered model to explain protocols and operations. They assist in protocol design because protocols operating at a specific layer have defined information that they act upon and a defined interface to the layers above and below. They foster competition because products from different vendors can work together. They prevent technology or capability changes in one layer from affecting other layers above and below. They provide a common language to describe networking functions and capabilities. Like the OSI model, the IoT reference model has 7 parts. The IoT reference model was developed as a common framework to guide and to help accelerate IoT deployments. The intent of the IoT reference model is to provide common terminology and help clarify how information flows and is processed for a unified IoT industry. As shown in the figure, the model breaks down the IoT concept into 7 functional levels, from physical devices and controllers at level 1 to collaboration and processes at level 7. The figure shows that security must permeate throughout all levels in the IoT reference model. Security measures include securing the hardware and software of each device or system connected to the IoT network, providing security for all processes that occur at each level in the network, securing the movement of data and communications between each level. In 2008, the IoTSec created an architecture for machine-to-machine communications, which also includes IoT devices. The purpose of the model was to provide a common framework for understanding the placement of various standards and protocols in an IoT system. The IoTSI model includes 3 domains, as shown in the figure. Application domain. This is where management functions can occur such as data analytics, connectivity management, smart energy management, fleet management, or any application that consumes data from IoT devices. Network domain. This is where data exists on the local network and is transported to the application domain using wired and wireless protocols, such as multi-protocol label switching, or MPLS, long-term evolution, or LTE, and worldwide interoperability for microwave access, or WiMAX. M2M device domain. This is where end devices, such as sensors, actuators, and controllers, connect to the network through M2M gateways using various protocols, such as Bluetooth. There are a variety of other special use IoT models that have been developed, including the following: Bridge model for control hierarchy. This is a common and well-understood model in the manufacturing industry that segments devices and equipment into hierarchical functions. Industrial Internet Reference Architecture is a standards-based framework used by system architects to design industrial systems. Internet of Things Architecture. Commonly referred to as IETA, this model is more formally known as Architectural Reference Model for the Internet of Things. The IETA is maintained by the IoT Forum. Simplifying the system by dividing it into functional areas is a very useful way to gain an understanding of complex systems. The figure shows a simple IoT model similar to the ETSI M2M standardized architecture. The ETSI model has 3 domains, each with a data management focus. Here, we convert those domains to application, communication, and device layers as shown in the figure. For example, the device layer of an irrigation system might include individual sprinkler heads, moisture sensors, temperature sensors, and actuators. At the communication layer, these devices might all be connected to a local irrigation control panel that monitors the state of the system. At the application layer, the control panel may be connected to a remote data center where all the control panels for multiple irrigation systems are aggregated. For data management, we are interested in when and where data is processed. Is it processed at the mist layer, close to the ground where things are connected to the network? For example, can the sprinkler for an irrigation system detect temperature and soil moisture and activate autonomously? Or is the data processed at the fog layer, on a local device that has more power, such as irrigation system's control panel? Can a supervisor remotely override the autonomous actions of the control panel using a mobile or desktop application in the cloud? Regardless of functional connectivity and data management aspects of the IoT system, security must permeate throughout, as shown by the arrow in the graphic. To better understand the placement of the more common protocols and standards used in IoT systems, this course uses a combination of the functional layers of the IoT simplified model overlaid with the TCP/IP model, as shown in the figure. The National Institute for Standards and Technology published the NICE Cybersecurity Workforce Framework in November 2017. The publication is an excellent reference for learning how to identify, recruit, develop, and retain cybersecurity talent. The publication clearly defines work roles that include the necessary knowledge, skills, and abilities required as well as the tasks performed by someone in the work role. The work roles are divided into 7 categories as shown in the figure. Skills and knowledge gained in this course apply to both the security provision and the protect and defend categories. Work roles in the securely provisioned category are responsible for conceptualizing, designing, procuring, and implementing secure information technology systems. In the securely provisioned work category, the risk management specialty area is the focus for this course. This includes all the processes necessary to assure that existing and new IT systems meet the organization's cybersecurity and risk requirements. Additionally, it includes the appropriate treatment of risk, compliance, and assurance from internal and external perspectives. The work role is Security Control Assessor. People in this role conduct comprehensive assessments of the management, operational, and technical security controls to determine their overall effectiveness. Work roles in the Protect and Defend category are identifying, analyzing, and mitigating threats to IT systems. In the Protect and Defend work category, the Vulnerability Assessment and Management specialty area is the focus for this course. This includes the following: conducting assessments of threats and vulnerabilities, determining deviations from acceptable configurations or policies, assessing the level of risk, and developing or recommending appropriate mitigation countermeasures. The work role is Vulnerability Assessment Analyst. People in this role perform assessments of IT systems and identify where those systems deviate from acceptable configurations or policy. They are also responsible for measuring the effectiveness of the security architecture against known vulnerabilities. Threat modeling is a tool used to conduct tasks for risk management and vulnerability assessments. Threat modeling is a structured approach for analyzing the security and vulnerability of a system, whether that system be a device's hardware, software, or the networks used to communicate with other devices. This course uses an adaptation of Microsoft Threat Model Analysis and applies it to an IoT system, as shown in the figure. Notice that the model includes aspects of risk management and vulnerability assessment. Step 1. Identify security objectives. The following categories determine the security objectives for the IoT system: identity, financial, reputation, privacy and regulation, availability guarantees, and safety. Step 2 documents the IoT system architecture. Create documents that describe the IoT system architecture, including components of the IoT system at the application, communication, and device layers, the flow of data between components and between layers, the technologies, protocols, and standards used to implement the IoT system. Use the documentation from Step 2 to dive deeper into individual components and features that impact the security objectives of the IoT system. The aim is to create a security profile that will help you identify threats and vulnerabilities in the design, implementation, and deployment of the IoT system. During this step, gather information about the IoT system using the following tasks: identify trust boundaries, data flow, entry points, sensitive data, and document the security profile. The purpose of Step 4 is to identify and rate threats. In this course, we will use two tools to identify and rate the threats and vulnerabilities. STRIDE is a vulnerability assessment tool used to identify threats. STRIDE is an acronym that stands for the following categories of threats: spoofing identity, tampering with data, repudiation, information disclosure, denial of service, and elevation of privilege. DREAD is a risk assessment tool and is used to rate the threats discovered in the STRIDE process. DREAD is an acronym that stands for the variables used to quantify, compare, and prioritize the amount of risk in each threat. After identifying and rating the threats, you must then determine the mitigation techniques for each threat and select the most appropriate technology that would reduce or eliminate the threat. During this evaluation, you must keep in mind what makes sense from a business perspective, including existing policies within your organization.